Okay, so in a collision of two particles, we summarize that F12 equals F21, and that's not true. It equals negative F21. The force exerted by the first mass on the second is equal and opposite to the force exerted on the second by the first. And I'm not sure I said that right, but you know what it means. Okay, so we conclude that A1 is F21 over M1, the force exerted on particle 1 by particle 2, divided by the mass of the particle on which the force is exerted. Similarly, A2 is F12 over M2, so that our change in the velocity v1 is equal to what? Well, equal to the acceleration times the time interval. Okay, now we're assuming, of course, that we have uniform forces, and that's not really the case, but it would be true of average forces as well. Okay, so, and also delta V2 is F12 over M2, and I think I've got the subscripts right, so, and that's negative F21 over M2, since F21 is a negative of F12, and then multiplied by delta T. So, we've already seen this. So what's the expression for magnitude of delta V2 over magnitude of delta V1? And this would be the ratio of how much the speed of the second changes to the amount that the speed of the first changes. Well, it's very straightforward. This is going to be F21 over M2 delta T, where I don't have the arrow over the F21 because now it's a magnitude. And this would be over this expression. Okay. Now, actually, your magnitude of delta V2 would be F12 over M2 times delta T. But since F12 has the same magnitude as F21, we can write it like this, and that's really pretty obvious, I think. If we simplify this, what do we get? Well, we get M1 over M2, which means the ratio of the velocity changes is the inverse of the mass ratio, meaning that the lesser mass has the greater change in speed. That's reasonably easy to understand. Okay, so it's an important idea. Now, I went and washed the board, and I don't remember everything that was on the previous, and I don't have time to check the video, but we could summarize. Yeah, okay. I know I didn't write this down. Okay. So, from this we can conclude that the net force multiplied by your time interval is the change in mv. Okay, we actually have that for either of our masses. So for example, for the first mass, we can see that we can rearrange this. Multiply both sides by m1, we get m1 delta v1 equals F21, the net force on that mass times delta t. And we can rearrange this to say the same thing. The product of the mass and the change in velocity is equal to the net force multiplied by delta t. So generally, we have this. Now, F net delta t has a name. It's called impulse. That's the impulse of this force through this time interval. And mv is called momentum. So this is change in momentum. So impulse is equal to change in momentum. Now there are qualifiers. I mean the impulse of the net force. So we could say net impulse is equal to the change in momentum of the particle on which it's acting. Okay? To which the impulse is delivered. Where we often use P for momentum. Can't very well use M, can we? Because we use that for mass and meters and lots of other things. So we're going to use P for momentum. That's the momentum. And let's be more specific. The momentum of mass M at velocity v is this. So now we understand how this is an expression. It can be expressed as net impulse equals change in momentum. And just to be clear, impulse is the force F. Acting for time interval delta t is F delta t. Then I'll just mention that if F is not constant, then the interval would be, the impulse be just an integral of F with respect to t from t naught, say, to t naught plus delta t. You just sum up all your F delta t contributions from the variable force. And another thing I'll mention here that I didn't mention in class, if you got force this way and t this way, if your force changes in time, then over any delta t interval, the impulse is the area under the curve. That would certainly be true if the curve was a horizontal line, because then you'd have this definition, but it's also true because the integral is equal to that area. And that comes down to trapezoids and so forth in a way that we haven't completely talked about yet, but that's really where it comes from. Or that's really how we're going to justify it in this course. And we'll talk more about that later. And then that one compare with F parallel delta S equals the work done on an interval. Okay? This is where you're multiplying your force by your displacement, or at least a parallel component of the force by the displacement, or alternatively, as you should know, the force by the parallel component of the displacement, depending on which vector you choose to project onto. This is a force acting through a displacement. This is a force acting for a time. Okay? This is a vector. Impulse is a vector because it's a product of a vector with a scalar. Work is not a vector. It's a scalar projection of your force times your delta S. and actually I should have put an arrow over the delta S, okay? This is scalar projection parallel, okay? And we know the details of how that's calculated. The idea is simply that this is a scalar, so maybe I ought to just get rid of the arrows over both this and this. This is a vector. This is what happens when a force is applied through a distance or displacement. This is what happens if a force is applied for a timing.